Okay, so now that we know the proportional areas theorem, let's go down here and apply it. So in example 1, it says the figures in each pair are similar. First of all, compare the first to the second. So by compare the first to the second, they basically mean write the similarity ratio. So we're talking about the similarity ratio here, similarity ratio, or in other words, the side compared to the other side ratio is 4 to 5. That's what it means to compare side to side, 4 to 5. Or you can write it 4:5 as well. So number 2, give the ratio of the perimeters. Well, that's pretty not too bad because the perimeter ratio, I keep doing that, perimeter ratio, is always the exact same thing as the similarity ratio. There's nothing to compute, there's nothing to calculate. It's automatically 4 to 5 because the side-to-side ratio was 4 to 5. And you know what, I'm going to write that a little bit different way because I want you to realize what that 4 to 5 represents is the perimeter of the first figure compared to the perimeter of the second figure is 4 to 5. So then number 3, write the ratio of the areas. And so the area ratios, we have 1, we have 2, and these are our first 2 answers. And then the number 3, the area ratio, that is if I were to find the area of the first figure compared to the area of the second. Now some of you right here are going, wait a second, Miss Benton, how am I supposed to find the area of this if all I have is one number? Am I supposed to assume it's a square? What am I supposed to do with that? And you know what? Here's the thing. It doesn't matter. It doesn't matter what shape it is. It doesn't matter if it's a hexagon, a triangle, a square. The area ratio is always this same ratio, this 4 to 5 that we already found. You take that and you square it. So written another way, this is the side-to-side ratio that we got earlier, squared. So 4 squared to 5 squared is just 16 to 25. That's your final answer there on part A. So it's a lot of work just for part A. You got to find 3 different things, but it's pretty not too bad once you know what you're doing. Okay, so what I want you to do is I want you to pause the video. You've got a U-try here. And I want you to use these theorems to find the similarity ratio, perimeter ratio, and area ratio. You should have 3 answers. And so pause the video and then come back and check. Okay, so we need the similarity ratio. I'm going to abbreviate this time. We need the perimeter ratio. And we need the area ratio. So for this first one, first of all, you got to figure out which sides are even matchy-matchy. If you're looking at this, orienting by the angles, let's see, seems to be the same side as the 5. So our similarity ratio, in other words, our side-to-side ratio, comparing the side of one figure to the matchy-matchy side of the other figure would be 3 to 5. The perimeter ratio, you're saying, Ms. Benton, I have no idea what those side lengths are. It doesn't matter because it will always be, these are always the same. These are always the same stinking number. Okay, and then the area ratio is the side-to-side ratio squared. If I want to know the area of this, even though I don't know any other numbers on it, I can still figure out what the ratio of the areas is, right? What the areas would have been if you'd taken their comparison, if you'd taken their ratio and then reduced it, that would have come out to be whatever the sides are squared. So that would have been 3 squared to 5 squared, which would have been 9 to 25. So you should have all 3 of these answers for example 1. All right, let's move on then to example 2. In the figures, the figures in each pair are similar. The area of one figure is given. Find the area of the other figure to the nearest whole number. So all we know is that the bottom of this big triangle is 12, the bottom of the little triangle is 5, and then we do know the area of the little triangle is 20. So we could work backwards to figure out what the height was and figure all that out. But that would be a lot of work now that we know this shortcut. We know a way to figure out the area of the big one, we'll call it x, because we know something about the ratios. We know that if the side-to-side ratio is 12 compared to the matchy-matchy side of 5, right? Here, I'm going to make this green here to make more sense. We know that if you take that and you square those numbers, then you get the area ratio. So I know that the 12 is to 5 squared will be equivalent to what you would get for whatever the area of the first one is compared to the area of the second one of 20. So how do we solve this? Well, it's just a cross multiplication problem. Now I'm going to make my life easier, I'm going to go ahead and deal with my exponents. So 12 times 12 is 144. 5 times 5 is 25. I'm going to do that before I cross multiply. Now I'm ready. 124 times 20. I think I just said 124. 144 times 20 gives us 2,880. And then when I cross multiply x times 25, I get 25x, obviously. I'm going to cross out this geometry Benton that's getting in our way. And now I have an equation that I'm trying to solve. I'm trying to get x by itself, and so I'm going to divide both sides by 25. So 2,880 divided by 25, x is 115.2. So what was that? That was the area. That was our area of the big triangle. So pretty cool that you didn't even have to know the height and 1/2 base times height to figure out the area of the big triangle. We could do it all with proportions. So we have another U-try here. Go ahead and pause the video and then I'll do the U-try with you in the next video.